when the current in one coil changes at a rate of 5.6 amps per second, an EMF of 6.3 millivolts is induced in a second nearby coil. What is the mutual inductance of the coil? Okay, so current in this coil induces an EMF in that coil. And you saw that the mutual inductance is defined by this equation. This is the rate of change of current in this coil. The proportionality constant is the mutual inductance. And what do you think is the negative sign doing?
Direction current flow.
Yeah. So if the current is increasing in this direction, that means the magnetic field is increasing in that direction and the induced current is in that direction. Okay? That's what that negative sign is related to. It's opposing the change. Okay, so here we'll just do this. Okay, so M12 is di1 by dt. Okay. So the magnitude of the proportionality constant is 6.3 into 10 to the minus 3 volts divided by 5.6 amps per second. And volts second per amp, what is that combination called?
It's Henry.
Henry. So this is an inductance. Okay, that's Henry's. So this is equal to, so this is in millihenries. So that's the mutual inductance between the two coils. All right, let me ask you this. So this was the rate of change of current in there, and that was the induced EMF there. What if I do the opposite? What if I pass a current through there and change the rate of current at the same rate here? What will happen here?
Current will be in the opposite direction.
The exact same voltage will be induced in there. Okay. So, yep.
Can you explain the direction of induction again? I don't
All right.
understand that.
All right, so let's pass this current in this direction. Okay, I'm going to increase this current. Okay, what is this current doing? So point your fingers like that. It's producing a magnetic field like so.
Okay.
Okay. So if I increase this current, this magnetic field will increase. That magnetic field is increasing in here. The magnetic field through this thing is changing, which will induce a current. And what is the direction of the induced current? It has to oppose it, because the induced field is in the opposite direction.
Okay.
And that's what this minus sign is related.
So are you pointing your thumb in the direction of
Yeah, so
the
you
B
point your fingers in the direction of the current and your thumb points in the direction of the magnetic field.
Okay, thank you.
Yeah,
Stress.
with your right hand. All right, I'll do it.
Okay, thank you.
Mhm. So, again, oftentimes this mutual inductance is hard to give because it depends on the distance between them, the orientation between, so you can't have a general formula for that thing. Yeah. If you have very special arrangements, we'll give you a formula for that. Okay, so one of the problems involves that. A 600 turn solenoid is 0.55 meter long and 4.2 centimeter in diameter. Inside the solenoid, a small single turn rectangular coil is fixed in place with its face perpendicular to the long axis of the solenoid. What is the mutual inductance of the system? So for this configuration, we'll give you a formula. Okay. So here's the solenoid. Okay. And what it'll do is it'll produce, when you pass a current through it, it'll produce a magnetic field like that. And what we're going to do is we're going to place a small rectangular coil inside. Okay. And so the magnetic field is perpendicular to that. Okay. What does Mr. Faraday say? What is the induced EMF in here? The induced, we'll call this E2. E2 is minus d phi, the magnetic flux through there. What is the magnetic flux through there? It's a single turn, so minus d by dt of B times area, A2. And we'll call this B1. Field produced by the solenoid 1, A2 is the area of coil 2. All right, so E2 is, and what is B1? B1 is mu naught N I1 times A2. So mu naught N, we'll call it N1 actually. So N1 is the number of turns in coil 1, A2 di1 by dt. Okay, so there is your mutual inductance. Okay, for this configuration. N1 is the number of turns in coil 1, and this is A2. A2 is the area of coil 2. Okay, if you change the orientation of this coil, this will change. Okay? So there'll be a cosine theta factor and so on. If you have N2 turns here, you'll have a factor of N2 here. Okay? And so on. So, yeah, to figure out mutual inductance case by case, and you may or may not be able to find a formula. Okay? A solenoid 50 centimeters long is wound with 500 turns of the wire, of wire. The cross-sectional area of the coil is 2 centimeters square. What is the self-inductance of the solenoid? And the self-inductance is mu naught. This is air filled L square A L. Okay, let me make sure of the formula. I believe it's correct, but it doesn't hurt to check. Mu naught, yep. Right, mu naught is permeability of free space, which is 4 pi times 10 to the minus 7 Tesla meter amp. N is 500 turns divided by 0.5 meters. Okay, so that's 1,000 per meter, 1,000 turns per meter. And the cross-sectional area is 2 centimeters square. And that's meter square, and length is 0.5 meters. So this is 1,000, square, that's 10 to the 6. That makes it 10 to the minus 1. And then there's 10 to the minus 4, 10 to the minus 5, and 10 to the minus 6. So we'll make all of this 10 to the minus 6, 4 pi into 4 into 5. And what is this mess of units? The meter meter square cancels there. Tesla meter square per amp, all that has to become Henry. So this is equal to 250 microhenry. Okay. A long cylindrical solenoid with 100 turns per centimeter has a radius of 1.5 centimeters. Neglecting end effects, what is the self-inductance per unit length of the solenoid? So it's mu naught n square AL. And what they want is the inductance per unit length. Okay? For every meter of the solenoid, this is how much the inductance is. Okay? Mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. N is 100 turns per centimeters. 100 turns, and 1 centimeter is 0.01 meter square. A is pi r square, and the radius is 1.5 centimeters, 10 minus 2 meters square. So this makes it 10,000. That's square is 10 to the 8, and then that becomes 10 to the 1. That's 10 to the minus 4, so 10 to the minus 3. And this will be, what will be the units?
Henry's per meter.
There you go. 4 pi, there's another pi, and then 1.5 squared. Okay, so 88.8 millihenry per meter. Now part B says, if the current through the solenoid changes at a rate of 5 amps per second, what is the EMF induced per unit per length? Okay, so the self-inductance is L di by dt. Okay. So the EMF induced per unit length is minus L over L di by dt. Why is this information useful? So inductors, so long coaxial cables will have inductance. So they want to know what is the EMF per meter. Okay. What is the inductance per meter and so on. So that's why this kind of stuff is useful. Okay, so we found this. L by L is 88 so EMF the magnitude is 8.88 into 10 minus 3 Henry per meter. And di by dt, the rate at which the current is changing, is 5 amps per second. So it works out to 0.4 volts per meter. Okay. At the instant a current of 0.2 amps is flowing through a coil, a wire, the energy stored in its magnetic field is that much. What is the self-inductance of the coil? Okay, so when this current flows through, that's how much energy is stored. Okay, so this is 0.2, so this is 2 times 10 to the minus 1. So that makes it, so 12 divided by 4, 1.2 divided by 4. Okay, 0.3 Henry. Okay, so when we close the switch on this circuit, what happens? The current rises exponentially. Okay? And what is the expression for the current? IT. Well, I like to use small I. The final value of the current, what is the final value of the current? It's as if this guy wasn't present. It would be E over R. 1 minus e to the power of minus t over tau. What is tau?
Our time constant of resistance per, or divided by inductance.
L over R. Yeah. Okay. Here's how you remember it. Greater the inductance, slower the rise, higher the time constant. Okay. It takes the current in the circuit. How long after a switch is thrown down does it take the current to reach half its maximum value in terms of the time constant? Okay, so you want t equal to infinity gives you the maximum value, so you want half the maximum value. Half the maximum value. You did something like this in lab, remember the voltage across the, okay, so e to the power minus t half over tau equal to 1/2 and minus t 1/2 over tau equal to log 1/2. Yeah, so at that time. after 70% of the time constant, it's risen to half its maximum value. All right, so similar problem. In the RL circuit shown below, the current in the RL circuit shown below reaches half its maximum value in 1.75 milliseconds after the switch is thrown. Determine the time constant of the circuit and the resistance in the circuit. Okay, so we'll take that expression from the previous problem. T half is tau log 2, So time constant is T half or log 2, 1.75 milliseconds divided by log 2. So the time constant is 2.52 milliseconds. And the time constant is L over R, so R is L is 215 millihenries, and time constant is 2.52 milliseconds. You see, the millis cancel, they're 10 to the minus 3, so, and henries over seconds is ohms. So this is about 100 ohms. Okay, so 99 ohms. All right, you don't have to worry about this problem, okay? So it's very messy. That was a little too ambitious.
A lot of blank pages.
What's that?
A lot of blank pages.
Yep. What is the self-inductance of an LC circuit that oscillates at 60 hertz when its capacitance is 10 microfarads? Okay, omega is 1 over LC. Omega is, which is 2 pi f. So omega square, it's 4 pi square f square, 1 over LC. L is 60 hertz. Hertz is 1 over seconds. And C is 10 microfarads. works out to 0.7 henries. So this is a circuit that would resonate with the frequency coming out of your wall socket. So you hook this guy to your wall socket, what will happen?
It'll explode.
It'll burn up pretty fast, yeah. What resistance must be connected in series with a 2 millihenry inductor of the resulting RLC oscillation circuit is to decay 50% of its initial value of the charge in 50 cycles to 0.10 of its initial value. Okay, so okay, so you set it in oscillation, and so this thing will, here's the expression. Okay, so the charge on the capacitor decays like this. Okay, so QT RT over 2L cosine. All right, so what do they tell us? So they're asking you what is the resistance in series with a 200 millihenry inductor to decay to 50% of its initial value. So this needs to become half. Okay? Half. This needs to become half in 50 cycles. In 50 cycles. Okay. Okay. See, the problem is actually, this cannot be solved because the capacitance is not given. Okay, for the frequency, you need to know the capacitance. Oh, yeah, I remember. You can't. So
Do you expect it to make any assumptions?
no. So we will give a capacitance value. How's that? Okay, let's make a reasonable assumption for the capacitor. Millihenry. Okay. Okay, 10 microfarads. Okay. So omega is, so what we want is e to the power of minus RT 2L to be half. So we want RT, take the log of both sides, is log 2. You want T to be equal to and what is T in 50 cycles? So T is 50 cycles, where capital T is the period. So 50T is 2L over R log 2. So we are given L, okay, and now what is T? T omega, which is 2 pi F, which is 2 pi over T, equal to 1 over LC minus R over 2L squared to the power half. Okay. All right, so we're going to substitute this value of T in here. So 50 times 2 pi over 1 over LC So we assume C, L was given, and R is the only unknown. So you can solve for it. It's a mess, and so we'll leave it at that. Yep. All right, guys.